Okay, so imagine for a second you're a librarian, but a really disorganized one.
Uh-oh.
Yeah, a total nightmare. You've got, say, 5,000 books, but you have no shelves. Just this massive, chaotic pile in the middle of the floor.
That sounds like a miserable afternoon and probably a fire hazard.
It's awful. And if I walk in and ask you for The Great Gatsby, you have to physically pick up every single book one by one until you find it.
Right.
And that's exactly how a lot of beginner code works. So today, we're moving from that chaotic pile to a perfectly labeled infinite filing cabinet. We're doing a deep dive into Chapter 6, Arrays.
And hopefully we're going to save you from that pile of books scenario. Our source today is a lecture presentation, Introduction to Programming Chapter 6. It's pretty foundational stuff. It covers everything from how memory is managed, which is surprisingly physical, to math, and eventually how to stop your programs from crashing.
The mission for this deep dive is pretty clear then. We want to really understand how programmers can handle lots of values efficiently. We want to see how arrays can replace pages of messy code with, like, one or two clean lines.
To maybe help you avoid that dreaded index out of bounds
Oh,
error.
absolutely. It's a rite of passage, isn't it?
It really is. If you haven't crashed a program by going out of bounds, you haven't really coded yet.
So let's get right into the anatomy of this thing. We hear the word array all the time, but the source gives us a very specific definition. What are we actually looking at?
Well, if you strip away all the syntax, the source defines it pretty clearly. It's a data structure that stores a bunch of values, all of the same type,
Right.
and they're all stored in what are called contiguous memory locations.
Okay, contiguous memory locations. That sounds a little textbooky. What does that actually mean for me when I'm writing code? Why does it matter?
It matters because it is the secret sauce. That's why they're so fast. Think of your computer's memory like a long street with house numbers. When you create an array, let's say for product prices, the computer doesn't just scatter those prices around randomly. It finds an empty block of addresses and puts them all right next to each other.
So they're literal neighbors, no gaps in between.
Exactly. No gaps. The source uses a great example. Imagine an array called prices. The first item, price is 0, is at memory address 1000. And let's say each number takes up 4 bytes of space.
Keeping the math simple. I like it.
Then the next item, price is 1, isn't at some random address. It's precisely at 1004.
And prices 2 would be at 1008.
You got it. It's completely predictable.
And that's the key word, isn't it? Predictable. The computer doesn't have to search, it just does the math and it instantly knows where to go.
That's it. If you ask for the 100th item, it just calculates start at 1000, add 4 bytes times 100, and boom, it's there. No searching required.
So that physical adjacency is the whole reason arrays are so efficient. You're not running around the library. You know exactly what shelf and slot the book is on.
Precisely.
Yeah.
But there's a catch that trips up almost everyone when they start. The numbering.
Yes. The famous zero index rule.
The bane of every beginner's existence.
The lecture really hammers this point home. If I create an array of, say, size 3, my brain wants to think of the items as 1, 2, and 3. But that's not right, is it?
Nope. And it's totally counterintuitive for us. We
Yeah.
count 1, 2, 3. The computer counts offsets. How far are we from the start?
So an array of size 3, prices 3, actually has indices 0, 1, and 2.
Correct. There is no index 3. If you try to access it, you've gone off the map. You're trying to read memory that doesn't belong to you.
The analogy I always liked is European floor numbers. You walk into a building on the ground floor, which is floor 0. The first floor is one flight up.
That is a perfect way to visualize it. Index 0 is your starting point. You haven't moved yet.
Okay, so we have our data all lined up nicely. What can we do with it? The source gets into a bit of arithmetic.
Right. And the slides try to make it clear that an array element isn't some special thing. It acts just like a normal variable. Number 0 is just a number.
So you can add them, subtract them, whatever.
Exactly. The source shows a few examples. They have an array called numbers, and they just do things like sum number 0 plus numbers 1.
Which would be 10 plus 20, so 30. Standard stuff.
Yeah. And then they show multiplication, product equals numbers 1, numbers 2, which is 600 in their example. They even show integer division with Python syntax.
So anything you can do with a regular number, you can do with an array element.
You got it. But, and this is big, but if all you're doing is writing number 0 plus numbers 1, you're kind of missing the point. You're still doing all the work manually.
Right. You're not using the power of the array.
Exactly. The real power comes when you combine arrays with loops. That's the engine.
Because you're not going to write 10,000 lines of code to add up 10,000 sales figures.
Never. You write one loop. You just tell the computer, start at index 0 and just keep going until you run out of numbers.
And the source points out some little differences between languages here, right? In how you know when to stop.
It does. The logic's the same, but the syntax changes. In Java, an array knows its own size, so you just ask for dot length.
Okay.
In Python, you wrap it in the len function.
And C++.
C++ is, well, it's a bit more old school.
How so?
You have to calculate it yourself. The source shows the formula, its size of numbers.
Wait. So you have to ask for the total memory size of the whole thing and then divide it by the size of one thing just to know how many things you have.
Mm-hmm. It feels a bit like doing your own carpentry just to sit in a chair.
Mm.
It gives you a lot of control, but it doesn't hold your hand.
Wow. Okay. Now, speaking of logic, there is a section in this source that I found really, really clever. The aha moment for me. It's about replacing these big nested decisions.
I agree. This is where you go from a beginner mindset to really thinking like a programmer.
So the source sets up a problem. You need to count how many times certain numbers appear in a set of data. Let's say the data is 0, 1, 2, 1, 0, 2, 2, 1, 0.
Right. Now, the amateur way to do this is to create 3 separate counters. Count 0, count 1, count 2. Then you write a big if-else block inside a loop.
I can picture it now. If the number is 0, add to count 0. Else if the number is 1, add to count 1. It's so clunky.
It's clunky, and it works for 3 numbers, but what if you have 100 categories? You're not going to write 100 else-if statements.
No way. It's
Mm.
unreadable, and you'd make a typo somewhere for sure. So what's the elegant array solution?
The solution is to use the value of the number itself as the index into a counting array.
Okay, unpack that a little.
So instead of all those if statements, you create an array called counts. And inside your loop, you write just one single line of code.
Okay.
Counts number plus CO. That's it.
Hold on. So if the number coming in from the data is a 0.
Yep, the code just runs counts 0 plus off. It goes to the shelf labeled 0 and adds 1.
Yeah, and if the number is a 2.
It runs counts 2 plus doc. It goes to the shelf labeled 2 and adds 1. The number itself tells you which counter to increment. No ifs needed.
That is so slick. It's like sorting mail. You don't look at a zip code and then check a big book to see which bin it goes in. You just look at the zip code and throw it in the bin with that number on it.
That is a perfect analogy. It's direct mapping. And the real beauty, as the source notes, is the scalability. That one line of code works for 3 categories or 3,000. You just need a bigger counts array.
You turn what could be hundreds of lines of logic into one. That's efficiency. Now, the lecture also brings up another concept called parallel arrays.
Yes. This is a common pattern, but it's a bit of a double-edged sword.
They used a burger menu example, right?
They did. So you have burger names and burger prices. With parallel arrays, you'd create 2 separate lists. One array, burger names, holds cheese, veggie, bacon.
And the second array.
The second array, burger prices, holds 5.99, 4.99, 6.99. The idea is that index 0 in the name list corresponds to index 0 in the price list.
So they're linked by their position. Cheese is at index 0, and its price, 5.99, is also at index 0.
Exactly. They're married by their index.
Mm.
But the source points out a big risk here. It lacks what's called encapsulation.
Meaning what? What's the risk?
It puts all the responsibility on you, the programmer, to keep them perfectly in sync. Imagine you decide to sort the burger names alphabetically.
Okay.
Now, bacon is at index 0. But if you forget to sort the burger prices array in the exact same way, bacon is now sitting at index 0, which still holds the price 5.99 the price of the cheeseburger.
Oh, wow. Yikes.
Yeah.
So your data is just, it's completely corrupted. You're selling bacon burgers for the price of a cheeseburger.
And you'd have no idea. The code doesn't crash. It just gives you the wrong answers. It's a really sneaky bug.
So it works for simple things, but you have to be super careful. Sticking with that idea of readability, let's talk about constants and the magic number problem.
Oh, the classic magic number. This is when you're reading code, you see something like temperatures 5 equals 76.
And you have no idea what 5 means.
Oh, is that 5 p.m.? Sunset number 5. Is it Saturday?
Which it was, in the source example, days of the week.
Exactly. Relying on your memory that 5 means Saturday is just asking for bugs. So the solution is to use named constants.
You just declare Monday 0, Tuesday 1, and so on.
Right. And now your code reads temperatures Monday equals 70. It's self-documenting.
Infinitely more readable. And safer.
It is. It's a small change that really separates professional code from hobbyist code.
I love that. Okay, so we've organized our data. Now we need to find things in it. The source covers the linear search.
The most basic search there is. It's like looking for your keys in a coat with a bunch of pockets. You just check the first pocket, then the next, then the next.
One by one.
Yep. You start a loop at index 0 and ask, is this what I'm looking for? If not, move to index 1, and so on.
The example was searching for the number 30 in a list.
Right. The code checks 10, no. Checks 20, no. Checks 30, yes. Found it at index 2.
But what if the thing you're looking for, say 60, isn't in the list at all?
Then the loop finishes, finds nothing, and your code has to handle that gracefully, usually by returning an INAX1 or printing a not found message.
Simple, but it gets the job done. Now this brings us to the final and maybe most important topic, the danger zone, bounds checking.
This is where most early programs die. We already established that for an array of a certain size, the valid indices are 0 to size 1.
Right, the ground floor rule.
The classic mistake is in your loop. If you have an array of size 5, and your loop condition says run while index is less than or equal to 5.
You've gone one step too far. The last valid index is 4. You're trying to access index 5.
And you're stepping onto a floor that doesn't exist. Now, the source breaks down what happens next by language, and this is really important because they act very differently.
So what happens in Java?
In Java, you're saved. The program crashes immediately with an array index outbounds exception. It's polite. It tells you exactly what you did wrong.
And Python.
Similar. Python throws an index error. Again, pretty clear you went too far.
But then there's C++ error.
And there's C++ error.
Yeah.
And the source calls what it does undefined behavior.
That does not sound good.
It is the worst possible outcome. C++ prioritizes speed above all else. It assumes you know what you're doing.
Right.
So if you ask for memory at index 5, it might just give you whatever random data happens to be sitting there.
Well, what data is that?
Could be anything. Another variable, part of your operating system, just garbage. And your program might not crash.
Yeah.
It might just start using that garbage data in its calculations.
So you could be calculating bank balances using random bits of memory and not even know it.
Exactly. Or, worse, you accidentally overwrite that memory and corrupt a completely different part of your program. It might crash 10 minutes later for a reason that makes no sense.
That is terrifying. It's like walking off a cliff in a cartoon, but you don't fall right away.
Yeah.
You just keep walking on air until you finally look down.
That's a great way to put it. In C++E, there are no guardrails. You have to be the guardrail. It's why understanding that size -1 rule is absolutely non-negotiable.
It's so interesting how the philosophies differ. Java and Python wrap you in bubble wrap, and C++ just hands you a power tool and says, good luck.
That's a fair assessment, yeah.
So to recap our journey, we started with arrays as these contiguous blocks of memory like houses on a street.
Then we saw how to use loops to process huge amounts of data, and how to use the data itself as an index to replace pages of if-else logic, that mail sorting trick.
And most importantly, we learned the golden rule. Stay in bounds. Do not visit the 5th floor of a 4-story building.
Especially if you're coding in C++ value. You remember nothing else. Remember size -1.
The big takeaway for me today is really about scalability.
I think that's the right focus. Arrays let you handle 5 items or 5 million items with the exact same code. That loop doesn't care how big the list is. And that's the core of computer science, solving a problem in a way that scales.
Now, before we go, I want to leave our listeners with one last thought. We talked about parallel arrays and how keeping the burger name list and the burger price list separate was risky. The source said it lacks encapsulation.
Right. It treats them as 2 separate things when really they belong together.
So, if arrays are just these raw lists of data, what happens when we want to treat the burger and its price as a single unbreakable unit so we can sort them or move them around together without ever messing up the data?
That is an excellent question. And if you're feeling the frustration of trying to keep those 2 lists in sync, you are feeling the exact pain that led to the invention of the next major topic in programming. But that is a topic for another deep dive.
I had a feeling you were going to say that. Thanks for listening, everyone. Go forth and array responsibly.
And stay within your bounds.